Hey, howdy back again. Welcome to the third video in the series on probability for middle school national curriculum. And have a look here. Where do we go next? We've been doing a lot of probability, and here it is again. But you must be questioning now, what can we do with probability? Let's go back again. So here, what can we do next? Okay, and here's the question. Can probability calculations help us in everyday life? Well, have a look at the top. Yeah. Card games, rolling dice. Excuse me, I've got a bit of a cold here. And maybe Monopoly. Working out your chances of winning and stuff like that. But I think we should look at probability in a bigger context, something more important. So come down here to this little graph, and it's a measure of grade 12s, year 12s, and whether they are at or above college preparedness in basic skills here. Oh, are they prepared to go to college? College Americanism for university. So are they prepared enough in year 12 to go to university? Excuse me. And so here you can see there are two graphs here. Maths is the bottom one and reading is the top one. And we can say from this graph that the percentage, so there they are, of people ready don't go above 40% in either maths or reading. 40% of year 12 graduates or less are really prepared to go to university in their reading and math skills. So your probability, oh, here we are, the probability of choosing a student at random from the year 12s in this particular study is 40% of choosing one who is prepared to do the reading required and the maths required at university. Well, that's interesting. So that could be used as a predictor for various things, couldn't it? And that's true. The life insurance people work on probabilities of how long someone's going to live, or in accidents, what's the probability of a person of a certain age having an accident. It's used quite a bit. So let's look forward to elevating our skills, if you like, and going to the next level. So come on down now. And this is something that we've seen a little bit in earlier videos, but here we are. Consider the spinner. Here we are, a spinner. The thing in the center, the arrow spins round. And what's the probability of spinning a red? We've done this before. There are three sectors equal in size, so all have equal opportunity of being spun to. So it's 3 out of 8. So you might say, well, not spinning a red, there are two ways of thinking about this. You could say, like the book has here, blue or yellow, and count them up. Blue or... oh, spinning a red, 3 out of 8. Sorry, I've circled the wrong one there. I really have, or ticked the wrong one. So 3 out of 8. Blue or yellow, you could add up these others and find you get a total of 5 out of 8. But there is a different way of thinking, W-O-T, a different way of thinking. And that is to say, well, spinning a red has a probability of 3/8. Not spinning a red is what's left, isn't it? You either get a red or not a red. So you could say that's what's left from 1. So you could say 1 minus 3/8 must be the probability of getting what's left. You don't actually have to count them up. You could use the fact that not spinning a red is what's left from 1. That's called a complementary event. An event which makes up the rest of the outcomes, or is made up of the rest of the outcomes. Interesting, isn't it? I really want to work with you over the coming videos on your what? Your way of thinking. That's what WOT stands for. All right, come on down, let's keep the journey going. So here we are. This is for your notes now. If E is an event, then the complementary event of E is the event that E does not occur. Okay, so here the probability of spinning a red plus the probability of not spinning a red has to come to 1. They're either red or they're not red. So there you have it, either red or not red. Okay, so they must add up to 1. So once you've worked out 1, that's probably a red, you can work out what the other one must be, because it must add up to 1. Okay, get the idea? Pretty simple. Okay, let's have a look. So what we did up before, what I was showing you before, if you have an event, the probability of not that event, E dashed, is not that event, or the complementary event, complementary event, the rest that aren't in E, is 1 minus probability E, because between E and E dash, you've got everything. All right, let's have a look at it in action now. Balls numbered 1 to 60 are placed in a box and 1 is selected at random. Determine the probability of selecting a multiple of 8 or not selecting a multiple of 8. Well, there are 60 balls. First of all, go back to the original idea. Excuse me. What outcomes are multiples of 8? 1 times 8 is 8. 2 times 8 is 16. 3 times 8 is 24. 4 times 8 is 32. 5 times 8, 6 times 8, 7 times 8. 8 times 8 is too big. So there we have 7 multiples. So chance of a multiple of 8 is 7 out of 60. Do you have to work out all the others? No. What's left? So if you've got a probability of a multiple of 8 of 7/6, just take it away from 1. So 53/60 is what's left, because 1 is 60 over 60. So take away 7/60, 60 take 7 is 53. So you get this shortcut way of finding what's left, if you like, the complementary event, E dashed. What's left after you take out the ones that you want. Okay, let's go down now. Let's do some here. I'd like you to go, excuse me, and have a go. Here's the notation. This means not A and not B. Okay, so given the probability, I want you to keep using PR, not P, unlike the book. These screen clippings are taken from Hayes and Harris. Very good book. I just like a slightly different symbol for P, for the probability, PR. Okay, can you go through and see if you can get somewhere with these half a dozen problems? Okay, and so what I want you to do is pause the presentation now for a moment, have a go, and then check your answers, or check some of them in between, perhaps. I'll go on now. Okay, so here are the answers to those 6 questions, and see what you think. I hope you're getting a few right. Okay, let's move on. Experimental probability. Now, this is interesting. What we've been doing so far is really theoretical probability, sometimes called, so I'll put that down, theoretical probability, because over here, theoretical, well, I can't read that very well, so let's get rid of that. Theoretical probability, theoretical, in theory, this is theoretical probability, or a priori, from the Latin, meaning before you do any checking, any tossing of coins. Can you work it out in theory? Yeah, well, if the coins are not weighted, not biased, equal chances of all the outcomes, equal chance of a head and a tail, you can work it out. Probability of a head will be a half, and the probability of a tail will be a half. This is the sort of work we've been doing. But sometimes, come over here, look at this. I've made a glider or a dart, whatever you want to call it, paper plane. And it's got 2 ways of landing. Right way up, which we hope, or wrong way up, upside down, which we don't want, particularly if you're on the plane. Oh, a bit small for Huddy, but anyway, that's right. So here, can we say that there's a half of each? Probability of upright, upways, up is a half, and the probability of landing face down is a half? Not really, because we don't know how we've folded those. You can't really tell there, whether it's going to have equal likelihood of being right way up or right way down. Okay. So how would you do it? Well, we could come up here, we could run an experiment. Do it many, many times and see what the chances are. So you do it, and the number of ups divided by the total number of ups over the total number of throwing the plane, would be the probability of an up. Experimentally, we'd do it and check it out. Okay, so we're going to have a little look at that now. For those situations where you don't have, over here, you don't have the idea or the definite idea that it'll be equal chances, so you can't work it out in theory. All right, are you ready? Come down now. Here we are. In a probability experiment now, so this is when you're actually doing it. Tossing a coin, rolling a die. The frequency of a particular event is the number of times that occurred, is observed. The relative frequency is the frequency of that event divided by the total number of tosses. So it's the same as a probability, and it's called a relative frequency. The frequency relative to or out of the total number of trials. So this relative frequency we can write as a decimal or a fraction, quite often as a decimal or a percentage. It will estimate the probability. Oh, now why is it only an estimate? I wonder if you can think about that. It'll estimate the probability. How do you work out the probability with experiment? Exactly, is that possible? That's an interesting question. I know in theoretical probability we can, because we say, well, the coin is unbiased, it's equal chance, the way it's weighted of being head or tail, then we can work out the probability, theoretically. But estimating here, they're saying we've got to estimate if we're doing an experiment. Why would it be an estimate? We'll come back to that. So here we are. Let's do it. A ball is thrown to Joel 40 times. He catches the ball 29 times. Estimate the probability that Joel will catch it or drop the next throw. Okay. So what's the probability of a catch? It's 29 out of 40. So probability of a drop is the relative frequency of a drop. It's what's left. That. Okay. So they're complementary events. He either gets it or he doesn't. So once you work out his chances of getting it, and that's the relative frequency by experiment, 29 out of 40, then you can take that away from one and say all the rest must have been drops. Okay, are you ready? Come along here. 15E1. Adam is practicing. Oh, here we go. That should be an S in English. The verb to practice has an S in it. The noun practice, when you go to practice, to the football or baseball practice, it's a C. So practicing there should be an S, but not to worry. So I want you to go through and have a look at this and see what you think. Again, pause the presentation, look ahead and mark your work. Remember, setting out is important. So the probability of something equals the relative frequency, something over something else. Work it out. It's not hard now. It's just a little bit of an extension of the basic notion of how many chances out of the total, except we're measuring them with an experiment. Do you get the idea? All right, let's go on now. Here are the answers here. Okay, so did you get these? All right, see what you think. Okay, let's keep the journey going. Here we have something. I wondered if you worried about that before. Why is it an estimate when we do an experiment? Why is it an estimate? Well, it could be many things. You remember the example with Maud with customers coming into the shop? She was trying to estimate the chance of her selling something. Well, depending on the day of the week, whether it was winter, you should take more days, shouldn't you? And do more experiments and take more data. Okay, so here, the more times an experiment is repeated, the more accurate the experimental probabilities will be. And we should also include other factors which might have an effect. Like, with catching a ball. Was Joel feeling all right today? Or was he a bit sick? Was the wind blowing a lot? How do you actually get your best estimate? You do it more times, and you also try to address more situations that could have an effect. Okay, getting the idea. The nature of how you set up the experiment is very, very important. Okay, come on down. Well, 15E2 here, just the same idea. And this time it's asking you to look at some of the other conditions that might be going on. Do you have to do more? Are just a few experiments good enough? And perhaps are there other factors? All right, so have a look at those four. Pause it and have a go. And here are your answers. Okay. All right, so have a look at what they're saying there. We're looking at the effect of the number of experiments on the reliability of the estimate. Let's get going now. Table data. Oh yeah, well this is often done, isn't it? When there's lots of data being collected. And here, a marketing company surveys 50 randomly selected people. Remember, randomly means everybody in the population has equal chance of being included. The population would be here, all the people who use toothpaste. So here we are. They want to see what toothpaste is most popular. So here's the brand, they list them down. Shine, they had 10 people wanted that. Starbright, 14 people. Bright, 4 people. Clean, 12 people. And a generic brand, maybe Black and Gold or something, 10. So, the relative frequency. Well, let's have a look. They haven't totaled this, so down here there was 50 there. Okay, so 10 out of 50 will be 0.2. 14 out of 50, etc. And they've changed them all to decimals. And this is handy if you want to say, well, the winning toothpaste was Starbright with 28%. Generally, people in the street don't want 0.28. Change it to a decimal by multiplying by 100. So the biggest market share went to Starbright with 28%. That's what the survey says. All right, so what's the probability they'll use Starbright or Clean? So Starbright, they've already done it. It's 0.28, the relative frequency. So the probability, our best estimate, is how many out of the total. And the probability of Clean is quickly behind them, close behind them, is 0.24 relative frequency, or 24%. And so we're going to say that's the probability. We quickly change from relative frequency to probability. But if it's an experiment, we know that is only an estimate. We can't work it out exactly. And classify these estimates as very good, good, or poor. Explain your answer. Well, they only took 50 people. Okay. There could be a lot more people using toothpaste than 50, isn't there? Thousands, millions use toothpaste. So very small sample size. We've sampled or gone and picked out very few people overall to represent the population of all toothpaste users. Can you see the idea now? I think you can see that. The same, I guess your teacher got you at some stage to toss a coin and do some experimental probability there. And if you did 10 tosses, did you exactly get 5 tails and 5 heads? No. By chance, you might have got even as much as 8 heads and 2 tails. By chance. You have to increase the number of experiments you do, or the sample size, if you like, what you're sampling, the results you're sampling. Okay, come on down, and here's your chance, 15F1, and I want you to work out the gaps in the table, so copy it in your book. Just remember, relative frequency is just as it sounds. It's a frequency relative to the total. It's the same as the chances out of sort of thing. only this time the frequency is the number of times it occurs out of the total number of experiments. It's an experimental equivalent to your definition of probability with expected number of things in your for making up your event over the total number of outcomes. All right, have a go, pause it. I'll show you the answers. Here they are. Okay. So just remember to put this quickly do. I didn't mention that. That means, I think we've seen it before, approximately. We should do that because we're rounding the figure off, for a start, to 3 significant figures. And of course, it's only an estimate. The probability can only be an estimate if we're doing it from empirical or experimental work, sometimes called empirical probability. All right, here we are. Let's have some more examples. 60 students were randomly selected and asked whether they studied physics and English. Let's have a look. So here we are. That's our table. So the total of physics was 28. Hang on, come down here. Completed. And the total of yes for physics and no for physics was 32. Totaling this way, yes for English was 27, no for English was 33. So it's a total of 60 students there. What does 13 in this table represent? Okay, 13 of the selected students study physics. Let's have a look. 13, there it is. Where is it? 13 of them study physics but do not study English. 13 is this one here. Yes, it's under yes for physics, but no for English. Yep. So you've got to learn to read the table of what box everybody's in, because it's a 2 variable thing, isn't it? English and physics. 2 different variables they're measuring, and it's discrete data. They're either yes or no for physics and yes or no for English, but there are 2 things being measured here. 12 out of the 60 students, okay, here we are up here, estimate the probability that a randomly selected student studies English but not physics. So studies English, where's English? Here's English, for yes for English, so there's 12 that study English but not physics. So it's approximately, because it's a relative frequency, empirical or experimental probability, 12 out of 60 is about 0.2. Estimate the probability that a randomly selected student who studies English also studies physics. So you want 2 yeses. So here it is in there. Yes under physics, yes under English. So it's 15 out of 27, and it's approximately, because it's being measured with an experiment. So the probability, and this is the 3 significant figures, we've rounded it off, is that. You get the idea. People put data in various forms. We've got to be able to read it and analyse it as budding young mathematicians. Okay, let's go on. Here we are. Next exercise from Hayes and Harris. You should grab that book. So you are to complete the table, get the hang of what's going on there by doing the totals of the rows and the columns. All right, have a go at those. We'll come down and have a look at the answers. We've got question 4 there. I snuck that one in before the answers. Question 4. And here are answers. Okay, 4 questions. So just make sure, do you understand the table? Can you read the table, reading the rows and reading the columns? Don't get mathematical indigestion. Read down one way, read across one way and then down the other to make sure you understand what's happening there. All right, let's go on. Now, probabilities from Venn diagrams. I don't know whether you've seen Venn diagrams before. Depends on what order you do the course. So here I'm going to take it that you haven't seen Venn diagrams. And Venn diagrams are a neat little way of picturing what's going on. So in this one, we'll go through this one. The Venn diagram shows the leg injuries sustained or obtained by playing by a team of footballers in their careers. Each dot represents one footballer. So here we are. We've got K is the knee injuries and A is the ankle injuries. Here we are. K and A. So we're trying to do a pictorial representation. So what does this mean? This is an interesting summary because this little bunch in here are just knee injuries. This little bunch in this circle are ankle, and overlap, they got both because they're in both circles. So get the idea of a Venn diagram? A circle is equivalent to the set of people who've got that characteristic, and you can have overlapping sets. So that's the intersection. So they have both. And then you have the box right out around it, which is called the universal set. U for universal set. So if they're not in those circles, it means they're not in either of the measured sets, but they are universally there. They're part of the big group that you were measuring. All right, let's have a look now at counting those up. We'll get rid of all this. How many footballers are there in the team? So that's a universal set. So we've got to add them all up. So we've got to add up the dots. There's 9 with just knee injuries, 4 with knee and ankle that are overlapping in the intersection there of the two sets, and 5 with just ankle, and 3 got no injuries, neither knee nor ankle. So how many footballers? There's 21. Add them all up. So the universal set here, excuse me, means the whole team. Now, if a footballer from the team is selected at random, sort of all the names in a hat, find the probability the footballer has had an injured knee. That's all your knees out of the total. So here are the whole set. 9 just knees, and 4 who also had ankles. It's a total of 13. So it is 13 out of 21. All right, there's no approximately here now because we did the whole team. We didn't do a representative group. We did the whole team. 5 players have had an injured ankle but not an injured knee. Okay, so that's this group here. Just in the ankle, not this group in the middle because they had both. Do you get the idea? So it's 5 out of 21. How many players, that was that, how many players had either injury? Well, we have the whole lot then. So either injury was a lot. They have knee or ankle or both. So that's what either means. One or other or both. So 9 plus 4 plus 5 is 18 out of the team, 18 out of 21. How many had both injuries? Those poor people are the ones in the middle here. I'll get rid of all this noise here. Now that's those. Both of them, see how they are in that set and in this one. They're in the, what's called the intersection of the two sets of people. Okay, so it's 4 and 27. Not a bad way of looking at data, is it? Pictorial. A lot of people prefer that to a table. So just have a look at table data. So there's lots of ways of looking at probability, and it's going to lead on to statistics. And they're very closely allied, aren't they? Okay, let's go on now. Another example. 30 tourists on a tour bus are discussing the countries they visited. 18 of them visited Japan, 11 visited Singapore, and 6 have done both countries. Represent this information on a Venn diagram. Okay, so you're going to draw a big set, and in the middle of that you'll have a circle for Japan, a circle for Singapore, and overlapping here will be both. So how many did both? 6. So put 6 in here. 18 have visited Japan. But hang on, 6 have done both. So what's left out of the Japanese? 18 takes 6. 12 have only gone to Japan. 11 visited Singapore. But 6 of those, so you've got to put this in first. 6 of those did Singapore and Japan. So 11 takes 6 is 5. So just watch, that's a tricky do there. You must really put in all the people in the middle who did both countries. Then take that number away from the rest who did Japan, because they're just in that hole, which are only Japan. Take them away from the number who did Singapore, so that that's 5. So overall, Singapore adds up to the correct amount, 11, and Japan adds up to 18. Do you get the idea? So you take them away because they are in both, if you like. So the idea there is to do step 1, put in the intersection. Those people who are in both, and then work out by subtraction what's in just Japan or just Singapore. Okay, now find the probability that a randomly chosen tourist on the bus has visited at least one. That's one or more. So it's all the people in here. At least one. So you can include the 6. I've done 2. So 12 plus 6 plus 5 is 23. And therefore your chances are 23 out of 30. All right, again, we're not putting an approximation because we're not talking about tourists in general. We're talking about tourists on a particular tour bus. Notice that you must not say, therefore, the probability of a randomly chosen tourist in general in Europe or somewhere will go to some place like Japan or Singapore is 23 out of 30. Then that 30 doesn't represent the whole population, does it? It would be an estimate, approximately. But this is exact here because we're saying on the bus of that bus only, the probability of choosing. Okay. Let's have a look at the last one. Given that a tourist has visited Singapore, or this has given us a condition. So we've got some information here now. We've got some information. We know that the tourist has visited Singapore. So the tourist in that bunch. So we're only going to look at that bunch because we have a condition. That is, it's only those that have visited Singapore. Find the probability that they have not visited Japan. So here, out of this bunch, focus on this, there's only 11 because we're told we're given that. It's a condition that we're given, so it's out of 11. And how many out of 11 didn't go to Japan? Well, those 6 did, so they are out. It sees 5. So we've got 5 out of 11. So this is called conditional probability because we're given some condition on the set that we're looking at. We're not looking at the whole lot. Hang on, we'll go back. We're not looking at the whole 30. We're told that we're given that they have visited Singapore. So we have a reduced sample space. Let's put that in. You're not too young to do that. We reduce the sample space. We don't look at the whole lot. We reduce the sample space. It's out of 11 now, not out of 30 because we know they are a particular group that have done something. We're told an additional condition about that probability calculation. Okay, let's have a look at 15G. I hope you're not getting too tired. It's good fun, isn't it, to do this problem and puzzle solving. So here are a couple of questions for you. I want you to, first of all, interpret the dots there and then draw your own Venn diagram. And don't forget, you want to do your conditional probability bit later as well. So pause it, have a go at this. Here's some more for you. Okay, look for those conditional ones where you're told something, and so now it's not out of the total, it's out of a subgroup or a subset of that group. Okay, pause it and have a go. And here are your last set of answers here. Those 5 questions. So I hope you're seeing the usefulness of it. Where does it all go? Well, it can analyse quite large sets of data. We use probably to analyse quite large sets of data to look at the makeup of the population or of the group that we're talking about and getting some idea of who we have to cater for. Okay, so it's exciting stuff and it gets better as we go on. And what's coming up next? Well, coming up next are the Year 9 topics. So if you've gotten through these first 3 videos, you have completed Year 7 and 8 probability according to the national curriculum, and you should be very proud of yourself. So I hope you have enjoyed that, and I will catch you in some more presentations as we go into year 9 and 10. Cheers for now.